It says explain how the IV characteristic shows that the resistivity of the semiconducting material decreases with increasing temperature. And then it says in your answer you should explain how you are aware that the temperature changes. Okay, a lot of people have struggled with this particular question, so I'm just going to go through it in a bit more depth than I would do normally. Okay, so let's have a look. So we've got the current on the y-axis and then the potential difference on the x-axis. Now resistance, okay, is voltage divided by current. Okay, if you had a graph of voltage on the y-axis and current on the x-axis, so the other way around to this, then the gradient would give you the resistance. Okay, but because it's plotted the other way around, the gradient, which I'm going to call m, is actually going to give you 1 over the resistance. So you need to be careful here. You can't talk about the gradient and link it to the resistance, because the gradient doesn't tell you the resistance in this case, because they've plotted the current on the y-axis and the potential difference on the x-axis. So the marks won't give you marks if you start talking about the gradient and saying that that's to do with the resistance, because it's not. Okay, so the first thing you do need to recognize is that this graph is actually, sorry, before I go on to this, one other thing I want to explain is that let's say this was voltage and on the y-axis and this was current on the x-axis, then like I've just said, the gradient will give you the resistance. You've got to be very careful. Say if I wanted to work out the resistance at this point, okay, resistance is the ratio of voltage to current. It's not the rate of change of voltage with respect to current. That's very important, because if it's a rate of change, okay, which it's not, so a rate of change would be something like, I don't know, distance with respect to time, for example. If it's a rate of change, then the gradient at a particular point is equal to the tangent, the gradient of the tangent at that point. Okay, so if this was, say, distance on the y-axis, time on the x-axis, you'd draw a tangent, okay, and then you'd work out the gradient of the tangent, and that would give you the velocity. But this is not what resistance is. Resistance is not the rate of change of voltage with current, it's just the ratio of voltage to current. So if there's a curved graph and you're asked to find the resistance, okay, then all as you would do is just read off the value for voltage, read off the value for current, and divide one by the other. You would not draw a tangent and work out the gradient of the tangent. That's a really important point that people often miss. You only draw tangents for things where it's a rate of change, which is not what resistance is. So going back to the question, the first thing you need to recognize is that this graph is a curved graph. If it's a curved graph, it means that the resistance must be changing, because a straight line graph with current and voltage, doesn't matter which way around they're plotted, if it's a straight line graph, the gradient, if it's a straight line graph, the resistance won't change. Okay, so the fact it's curved means the resistance must change. That's the first thing you should note down. And why is it curved? You'll need to explain why it's curved. It's because the current is going up faster than the voltage. It's not the other way around. It's not the voltage is going up faster than the current, it's the current's going up faster than the voltage. And if you don't believe me, you can take any 2 points. So if you take, 20 milliamps, 40 milliamps, you read off the voltages, the current's doubled, but the voltage won't have doubled, it'll be less than double. Okay, so current's going up faster than voltage. We need to kind of try and explain why the current is going up faster. So because the current is going up faster than the voltage, okay, the resistance will decrease. Okay, so if the current's going up faster than the voltage, the resistance will decrease. And then why is the current going up faster than the voltage? Well, it's all linked to the temperature of this semiconducting material. Okay, if I just briefly explain how a semiconductor material works, you've got what's called the band gap, and then you've got kind of charge carriers like electrons. They can't cross the band gap unless they've got enough energy. Once they have enough energy to cross over the band gap, then current can flow through the semiconducting material. Okay, so there's usually like a minimum voltage, and once that's achieved, these electrons have enough energy to cross the band gap and current can flow through the device. This is quite a simplistic overview of how it works, but it kind of gets the general point across. Now the effect temperature has, if there's a higher temperature in the if the semiconductor is at a higher temperature, more of these electrons can cross the band gap because they've got more energy. Okay, because of this thermal energy they've picked up as extra energy because they're at a higher temperature. Then you get more electrons that can cross over the band gap, therefore the current goes up. And that's exactly what's happening here. The temperature of the semiconductor is going up, more charge carriers are crossing the band gap, the current goes up. If the current's increasing, the resistance must decrease. That's just by definition. If resistance is opposition to the flow of charge, if there's more charge flowing, so more current, the resistance must go down. Okay, but what we've got to explain in our answer is why the temperature, why that is increasing, and it's all linked to this equation: P equals I squared R. Okay, this is the power equals the square of the current times the resistance. Now this equation is used for power loss due to heating. That's where this equation is normally used. So the power in this case is the power lost due to a heating effect. So electronic components, or wires, or in this case semiconductors, okay, there is a heating effect, and there's a strong dependency on the current that causes this heating effect. And it's why if you have kind of transmission lines from power stations, it's why those transmission lines transmit the power at a very high voltage and a very low current, rather than a very high current and a very low voltage, because the higher the current is, the more heating effect you got, the more power you get that's lost due to heating. Okay, so what happens is, if we look at this, if we look at the y-axis, as the current increases, so as we go up this y-axis, there's going to be more power that's lost due to heating, therefore the temperature is going to go up. Okay, so as the current increases, okay, there's a higher there's an increase in temperature because of this I squared R relationship. So as the current increases, there's more power loss due to heating, therefore the temperature is going to go up. And we've just explained that if the temperature goes up, we get an increase in current, therefore we get a drop in resistance. Okay, so let's try and write all these points down. So the first point we discussed is that the graph is curved. So graph is curved. So what can we say? If the graph is curved, so R changes, the resistance changes. It's not constant. We've said that if it's a straight line graph, the resistance doesn't change, but because there's a curve, the resistance changes. Okay, let's try and just justify that. We've got to say that I increases faster than V, and we've said that. We said the current increases faster than the voltage. That's why there's this curve. Okay, next point, we need to talk about the temperature. So the increased temperature is caused by a larger current. It's caused by larger current. So we said that when there's a larger current flowing through the device, the temperature increases because of that relationship P equals I squared R. So I would then state the equation, so P equals I squared R. Okay, that's my supporting point. That shows, so if we've said increased temperature is caused by larger current, that's shown by this equation. That's why I've stated this equation. Okay, because this equation shows there's a strong dependency for this heating effect, which is going to increase the temperature. There's a strong dependency on the current. Okay, so larger current, bigger heating effect, more temperature. That's what this equation shows. So this fourth point is supporting my third point. Okay, then you just need the final point, because remember the question is linked to resistivity decreasing with increasing temperature. So as R decreases, rho, which is resistivity, okay, decreases as well. Okay, so remember we've got the equation. We've got rho equals RA over L. A is not changing, L is not changing. So if our resistance has gone down, and that's this whole procedure we just talked through, we've talked that through the fact that resistance has gone down. Okay, if resistance has gone down and A and L stay the same, then the resistivity has to go down. Okay, so this question is actually quite tricky. It requires quite a lot of sort of in-depth analysis of how semiconductors work and how the temperature increase is caused and what effect that has on the semiconductor. Okay, but if you work these points through, these are the points from the mark schemes that are going to get you the full marks for this question. So just to quickly recap, the graph, as we saw, was curved. That means that the resistance has got to be changing. To explain the curve in more detail, so why is it curved? It's because the current increases faster than the voltage. Okay. Then we need to explain why there's a temperature increase in the first place, and that's because of the larger current that flows through it. So as the current increases through the semiconductor, the temperature is going to increase. The reason why that happens is because of this equation, P equals I squared R. This P refers to power loss due to heating effect, and it has a strong dependency on the current. So as there's a larger current flowing through the semiconductor, there's more power loss due to heating, therefore that's why the temperature goes up. And we've said that if the temperature goes up, okay, the current through the device goes up, because we said, remember, more charge carriers cross the band gap and the current goes up. Therefore, the resistance has got to go down if the current goes up, by definition. And we've seen by just looking at this equation, if A and L are the same, which they are, the cross-section area and the length, if the resistance goes down, therefore the resistivity has got to go down, which answers the question. Okay, I'll just stop this part of the video because we finished question 1. Hopefully all that makes sense, and then we'll carry on in part 2.